Today we are talking about symbols and footprints, and because it goes right hand in hand with it, libraries as well. So to get started, we've already got a thing here for us. We've got a pretend little circuit, at least something to kind of keep kind of half a leg in reality a little bit. So we've got a pretend project here where we've got about 40 LEDs here that need to be lit. We've got a power input here. We've got some kind of a trimmer pot or something here so we could dim the lights if we wanted to. What we need to have is a device right in here that's going to regulate the power down so that we could go from whatever we're plugging in here. Let's say it's a power brick or something like that of 12 volts. We need to be able to knock it down to something manageable like the 3.2-ish volts that the LEDs are going to require. So without digging into it any further than that, because reality would have to have that, we're going to go ahead and jump over here and show you the data sheet. So the data sheet for the device we're going to pick out is LD1117A from ST Micro. This is pretty common TO220 3.3 volt regulator right here. Kind of goes hand in hand with the 7805s and such, right? But what we want to see is right down here, we have the TO220 package that we are getting, let's say. And if we look at it, we'll notice that we have in, out, and ground are right here, which is a little bit different than most. A lot of them will have in on one side, out on the other, and ground in the middle, okay? Then also a thing you want to pay attention to, just a small little tangent, is that the tab of this particular one is not ground. It's very common to have the tab be ground, as you would imagine. Well, this one here is actually V out. It's the output right here. So if you accidentally were to nail this down in your circuit board thinking it's ground, so you connect it to a flooded ground plane to create heat dissipation, kind of like a weak heat sink of sorts, right? Yeah, you'd end up with some problems there because the output of your regulator will be going right into your ground plane. So probably not a good thing. But this is what we're after, at least for starters, for the symbol that we're going to create, because we're going to create a schematic symbol, and then later we're going to create a footprint, and the footprint information we need is down, 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 down. Here we go. So for a TO220 package like this, here's all the physical dimensions that you want to have, so you could make the holes, in this case, in the PCB so we can put this into it. And then you have to decide and then allow for, are you going to have this thing sticking up in the air? And if it's sticking up in the air, are you going to put a heat sink on the back of it? Or are you going to bend it over down flat onto the PCB? And then if so, are you going to put a hole through the PCB so that you can put a screw through it? Or are you going to leave some copper here that's not grounded in this case, that you could stick it to try to create a little bit of a heat sink? And will you be sticking it out with some thermal adhesive? That part, all that is maybe not super relevant, but if you are laying it down on the board, then you'll need to, in your footprint for the PCB, you'll want to create a little square here that denotes that that's what's going to happen so you don't accidentally put other components in its place. You see? So again, for starters, we'll go with this. So to get to your schematic symbol editor, you open up your schematic editor, which is a schema. I just don't say it that way. So that's, let me shut this down again so you can follow along. So you go here, schematic first. You double click on that, it opens up this. Then you go here to create, edit, delete symbols. Okay. And okay, so here's all the libraries that are currently in our system, in our application. And these are loaded either by the application or by you, and snafu that happened in the last video with my upgrade to 5.0, all my libraries disappeared, so I had to go download them from GitHub and put them in manually, right? Which briefly had to do with this area right here. So these are the separate libraries, and you would end up browse libraries, you'd go find them and add them in by hand. Thankfully, you can do multi-select and bring them all in. Okay. This is a bit unruly, by the way, and so I don't know, probably a video somewhere along the line talking about loading these and getting rid of them, because there's a lot of stuff in here that you don't need. And you can get it when you want it. So we're going to make a new symbol. So I know we clicked on the symbol that looked like that before. That got us to the editor. Now this is the one that's actually going to let us start making the new shapes. It basically, this is like a graphics program. You know, if you look over here, they're grayed out. We've got pins, text, and some shapes, right? That's really all we got going on here. The tricky part is knowing what pins are which, because you got to go check your data sheet. So I hit this to create a new symbol, and it wants to know what library you plan on working in. And if you go through this, well, we don't have a library yet, so we've got to make one first. And that's not hard, no big deal. It can all be done right in here as well. So to create your library, you're going to go over here. You see, so this one right here is create a new library. And when you click on it, it's going to open up your browser. Now you don't want to store it inside of your working folder. So this folder right here, directory, is where our current KiCad project is stored. So if I go here to KiCad projects, this is, you see, here's all the projects in here. This is a great spot to put your libraries, but you don't want to just leave it here called new library in here. You want to create a folder, and you're going to call it libraries. So if you go ahead and you make one library, you can put all your different components in that. But if you start making more and more and more of these, it might be kind of nice to separate this thing out a little bit so you don't have one library. So you'd go over here to the side here, you'd pick it, and you'd hit the little arrow over here, and it would expand out, and you might have, you know, 100 or more symbols inside there, and you're scrolling and scrolling and scrolling looking for, you know, an IC schematic or something, right? Well, maybe you make one library called ICs, and another one called power, and another one called passive or something. Something, you know, maybe initially fairly broad that you could store in, or just leave it as one called My Libraries, right? Now, one thing I think that you should do is, because this alphabetizes it, I've been doing things like this. Give it a plus sign or some kind of a character, and you'll see in a little bit, it will alphabetize this. And we won't have to go scrolling and scrolling to try to find it. The next thing is, do you want to make this a global or a project-based library? And for the most part, I can't think of any reason why I have ever needed to do a project-based library. I put them all global, and then I keep this directory in this project folder. This project folder, as a matter of fact, the KiCad folder, my real KiCad project folder, is on a memory stick that I have, because I don't have any one particular computer that I sit at when I'm working on things. So anywhere that I'm at, if it's got KiCad loaded on it, then I can put in the memory stick, and I can go to my KiCad projects, and I can start a new project, and then I can link it to the libraries that are in that memory stick. And then again, if I take it somewhere else, then it's basically still there. So this is going to be global. And then you see what I'm talking about right here? Plus sign libraries. It alphabetized. Otherwise, the whole exercise, we're going to be scrolling down here to my libraries every single time. All right. Libraries is there. It doesn't have a little arrow next to it because there's nothing in it yet. So now we can come to create a new symbol, and we pick library right there because that's where we're going to do it, and hit OK. Then you get this. So now it wants to know the symbol name and the reference designator. So if this is going to be a regulator, you know, what do you want to call it? So this is kind of like maybe your human name. What are you going to recognize it as when you're scrolling through your library list? So would you call it reg number 7? Probably not. You might want to call it, you know, maybe reg, you could call it an 1117. But that might not jump out at you as what you need. So you might say something like 3.3 volt, and then maybe 1117. Okay? Then the designator, when you go to annotate, when you have like R1, R2, R3, C1, C2, etc., this is that value. So again, maybe we'll just leave that as reg. And then you hit OK. After you do that, it just sort of smashes everything right over the top. So move those up and out of the way. These you can kind of place them where you want them, but if you rotate the component, when you're back out in schematic editor, it kind of moves these things around. So I wouldn't worry about them terribly too much. And if they irritate the crap out of you, you can edit them and you can make them invisible. And so then it will be basically hidden, sort of. This is more important when it's out in the schematic, when you're working with the PCB. You'll have elements that are important to you, so it shows it to you, but it won't actually be printed on the silkscreen. Okay, down to business. We have, again, where's my data sheet here? So we've got 3 pins. We've got in, out, and ground. And this one doesn't have them numbered, but if you look at all the other ones here, they are numbered. And if you're going from left to right, it's 1, 2, and 3. So you see this over here? So in is 3, out is 2, ground is 1. Also a little bit different. You know, that's a little bit different than maybe what people would expect, which is why, again, you've got to go to find the data sheet. So you come over here, you find yourself a pin, and you just click somewhere, because you can always move it later. And then right about here, when I was making these videos, when I was first starting, I probably started like umpteen times. You get to here, and I'm trying to make a real simple video. Click, 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 go, go, go. And you get to here, and you say, well, what's the pin name going to be? And I'd have to say something like, well, I don't know, you just make it up, or it'd have something to do with something, right? Well, this is the reason for the complication is because you need to know the data sheet. That's what the whole thing is. It's got to have a data sheet connected to it. Otherwise, everything's imaginary. So you look at this. Well, what are you going to call it? It's called input. Do you see? So this is the name of that pin right there. So the pin name, input, and it's going to be pin number, what? 1? No, 3. Pin number 3. Let's stick it. This is kind of the wording here is kind of weird. We want to have it up, which is actually pointing down. And then the input, the electrical type is an input, but if you scroll through here, there's actually a power input, so you can pick that as well. It's not horribly important, but you could just make them all be passive. These things have to do when you're doing the electrical rules check, that it will check it to see if, you know, the output of one device is going to an input of the other, right? That's you know, what it's for. And you can look up more online. I'll try to maybe post it somewhere on what these things actually do and what they mean as far as, again, the electrical rules check is concerned. So do that and call it good. There's our pin. This one's going to go over here. I always work off a center here. You don't have to. And so then we'll do another one. And this one here is the next one. So that's going to be an output, or it's going to be named output. And it is pin number 2. That's a power output. Okay. There you go. So you see, this is not terribly too hard, right? And then the last one we'll call ground. And it's pin number 1. Now I believe ground is always considered to be a power input. So we'll go with that. And again, like I said, if you ever have any problems with it and you're having a really tough time because design rule or electrical rules check is kicking your butt, change some pins to passive and see if that helps. There you go. So really, that could be my footprint. That could be it. That's all I really need to have. Because what's going to happen is these pins 1, 2, and 3 are going to get mapped to the PCB footprint, pin 1 to 1, 2 to 2, and 3 to 3. And so the two have got to go hand in hand so that you can wire your board properly. Okay? That will become more clear, of course, as we go on. But to make things look a little bit nicer, it's pretty common. Make a box around it. Oh, what? Okay, try that again. Go right to here. Looks even. Even. Click. Okay. If you want to make it look a little bit nicer, you don't have tons of options, but you gotta, if you hit edit somewhere in here, it doesn't, I'm hitting E on the keyboard, it's not working. If I hit E right over the line, you'll get the rectangle properties. You can change the width of the line, and you can fill the foreground or fill the background. It does not give you a color choice. So if you fill the foreground, it's all red, like the color of the line. If you get right over the line again and hit edit, fill the background, this probably is more common, you get the yellow cream color. So that's pretty much it. That's pretty much it. Yeah, I don't think that there's anything more that is worthwhile to talk about at this point. So when you're done, you're going to go ahead and you're going to come up here and save it. So that's done. When we place this though, I want to show you something else kind of cool that you can do that's been kind of handy. So we're done. That's our regulator. By the way, you didn't have to put the pins all down here at the bottom. I'm just kind of going along with the actual regulator. Some of these logical symbols, schematic symbols, will have in on one side, out on the other, and ground down below, right? But do it how you like. Then you close it, and then you're back here. Okay, so to place this thing, we'll go over here to our place symbol, and we'll click here. And now when this pops up, do you see, by the way, why I named it with a plus sign? Because it's up at the top everywhere I go. We hit the drop down, and then we've got our reg 3.3 volt 1117. There is our schematic. Hit OK. There you go. So that is, well, part 1 and 2. So we made a library, and we made a schematic symbol. Next thing is now to make a PCB footprint. But one more thing before we run over there, I want to show you on the schematic, once you place it, now you can hover over it, hit E for edit, or the long way, you just go properties, edit properties. See the E right there? And you'll get this window. So for the most part, it's fine as is, but there's a couple things that are kind of handy, really handy if you utilize it. Right here, we've got footprint and data sheet. Well, we don't have a footprint yet. We'll talk about that. We'll come back to that. The data sheet we do have, though, and the field value. Let me show you this. So here's the field value. You could copy this and you could paste it in your computer, or you could just copy this. You could copy the whole URL and paste it in there. There's the whole URL for that. And if I hit show data sheet, well, you can't see because it just popped up off my screen here, but there it is. So now, isn't that handy? Anytime you need to consult the data sheet for this particular part, you've got the data sheet to the manufacturer up there online. So you might want to be pretty mindful about how you name this value, because this does go straight to the actual, this particular company's data sheet, that model there. And so if that's the way you want it to be, then you might give this an actual, manufacturer name in there as well. So I hit OK to this. After we make a footprint, there's an association thing that has to happen in the software here. And it's kind of nice if you add the footprint right here, we'll tie the two together. Kind of cool. Then the last item on our list is to go make a physical PCB footprint that we're going to tie or associate this one to. And that's going to be a little bit different. So we're going to go up here to Footprint Editor. Open that up full screen. And then that is where, let's get down here. Zip, zip, zip. This is where we're going to need this. So we got to figure out where's their table at here. So here's our table, and then we got to correlate that with all the dimensions right here. And that's going to take a little bit more time. So we'll go ahead and use this one here in the schematic editor. We'll click this, and it will bring you up your footprint editor. Now, just like in the schematic symbol editor, you're going to need to, well, you're going to need to tell it the active library that you're using. But if you hit select active library, again, there's no library here. Now, you could have separate libraries, one for schematics and one for footprints and one for your 3D objects, which are in the 3D viewer. But I think it's kind of best for all of yours. You make the call there. I keep all of mine in the same location. Now, in order to tell it where that location is, instead of making a new library like we did in the schematic symbol editor, we're going to come up here to preferences, and where it says manage footprint libraries, what you're going to do is you're going to browse the libraries. You're going to browse directories looking for a library location. So you're going to look here under your KiCad projects, and you're going to look for not, again, the one that you're currently working on, symbols and footprints, not where our stuff is, not lab 1, that was from the other video. You want to pick your libraries folder, okay? Now, by the way, I wanted to mention that, again, that I'm running Linux, so my browser looks different than anybody else running Windows or Mac. So you will have to understand, hopefully, how tree structures work, how directories work, and, files, folders, and such. The concepts are same across the board. So you go ahead and select libraries and hit OK. And now in your path table right here, it will show down here the directory, the path to where your libraries are. Now you can go ahead and hit OK, but it might again be wise here. I'll show you here. So you come here and then you can say select the active directory, and now we've got to scroll through until we find there, right? That is why. Now you could do this. Too many things to talk about. Here, watch. Move it up. Move it up for days. Here, click, 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 click. Oh my God. Okay, so now we're all the way back up here at the top. We hit OK. You come back here, pick the active directory. Oh, it's still not there. What? No, that didn't do any good. So, oops. Here. Come here. Go to this. Pick that. Do this again. Hit that. Come back here. Looky. There you go. So exclamation mark, plus sign, any of the symbols above the numbers there, or a number, it will put it up here to the top. So go ahead and pick your libraries. Hit OK. And now you can start making the footprint. So then to actually start creating, you have a few buttons up here. This is going to be the one we're going to want. You could have one using a wizard, or you could load a footprint from a library. So this was kind of a thing I used to do every now and again, would be to load a footprint from some other library, and you basically like it, but you want to modify a couple things about it. You modify it, and then you save it in this current active library. Okay, well, we're going to go ahead, hit this one, and make our own new footprint. When you do this, it's going to ask you to give it a name. This is the name that's going to show up in the library. So if you need to use it again, if you can imagine, in a minute, we're going to associate our schematic symbol that we made to a PCB footprint, and that PCB footprint's going to have a name. So name it something understandable. Okay, so probably, again, this one will be called, well, I could call it 3.3 volt regulator. I could call it regulator. I could call it 1117, right? Now imagine you've got a bunch of different items in your library that you're looking for that are of a similar type. Where would you want to be looking for a 3.3 volt regulator? Would you want to be looking under everything that says 3.1, 3.2, 3.3, 3.3, 3.33, and the reason they say so many is because, it's a 3.3 power source. It's a 3.3 something or another. Oh, it's a 3.3 regulator. So it probably doesn't make sense to name it 3.3. It's probably going to be, you could call it regulator, if you want. Should we call it that? How about that? We'll call it regulator, and then the next classification after that. So maybe regulator dash 3.3 V if you want, dash, yeah, we'll do the 1117. And again, as I said with the other one, if this one is very specific to the make and model number, then include that as well. If you're making a lot of different things that have various, 3.3 volt regulators, but they come from different companies, I don't know why that would happen, but make sure you're very specific about how you name them. Okay, so I think that's probably an okay enough name right there. So hit OK there. And there is our information just like we saw before. And so I will get it out of our way. How far you move it out of your way, well, it depends upon how big you're going to make this, of course. But this is where the grid here that we haven't talked about yet is going to come into play. If you look up here, right now the grid, the dots are 0.1 millimeters apart, right? And you see that? This from here to here is not 0.1 millimeters. Kind of use some judgment, I guess, in a way that this right here, the link from here to here or so, is not going to be 1 millimeter. These are not a tenth of a millimeter apart. So you zoom in a little bit more, like, no, I think those are maybe it. And I think, oh, hell, damn. Okay, right? So you see these right here is the grid separation. Anyways, I didn't need to go into that completely quite yet, but just know that kind of gives you a size scale. Right now, these are probably, well, if you want, you could just set it over here to 1 millimeter apart. And you notice how nothing really changed, but if I zoom in, they don't get smaller anymore. So the default zoom level, they were 1 millimeter apart to begin with, but they had, in a way, like 10 separations between there, right? Anyways, our part is probably going to be about this big. Seem okay? Moving on. Now, as far as the starting point goes, we need some pads. So I think that might be an okay place to start. We know that it's going to be a through hole, so they're going to have to be that. Well, let me show you here. So here's a pad. I come out here and I place it. And you say, well, yep, that looks like it's going to be a through hole pad. But if you hover over and hit E to edit, what you can do, they all kind of start out this way, but you can say, no, it's an SMD, and it's not circular, it's rectangular, and it's not, 1.5 by 1.5. I could make it be, 3 by whatever, you see? And so anyways, that's our pad. Also in there was the size, the diameter of the thing and the hole. Okay, so we're going to need 3 of these, and we're going to need to know the spacing. To make life easier, I am going to go ahead and place them on the center line here, and I'll move this one up here. I'll explain in a second here. In the center, down here, if you look in it's got the X and Y coordinates down here. Remember how I was showing you this before, that if you look at this, and this is kind of different down here. It shows you the radial distance here when you do the spacebar 0 thing. I'm not really sure why they decided to do that. I'll have to think about that, why that's a good thing. At any rate, if this is the 0 point origin right here in the center, and this line being 0, it becomes pretty easy for me to know how to place the rest of this component, right? It might be different for other ones. But if I know that the pins are going to go here, and let's scroll this down here, roll it down here. By the way, zooming again is the scroll wheel, and panning, we call this panning. That's just holding the middle mouse in so you can move it around. So you don't have to try to keep zooming. Oh my God, right? Just get it where you want it and then grab it and bring it down. So if I know that the body of this is going to actually, let's say we're going to lay it down on here, and we know that we have a dimension in our data sheet that's going to say how big it is, it might be kind of easy to go, if this is 0 and the height of this thing is, say, 12 millimeters, then I could just draw the box up here. And the box, again, it's a graphic, but it's an indicator to us on the PCB to not place anything else there because we're going to lay this component on it. Okay, so we need to get some specifics. We need some hole sizes, and after we get the hole size, then we can kind of come up with the diameter. The yellow part here is actually the copper that you're going to solder to. So you can almost make it as big or small as you want, you know, sort of, kind of. You look at it, you know, in a way, you kind of got to make a couple boards, and then you decide, you know, how big you want your pads to be. And I know that there's certain ones that are, it's kind of like a standard on, you know, all PCBs that you ever soldered onto. You'll notice there's kind of a standard. But you might go, well, you know, I'm not really that good at soldering yet, or this is kind of a tough surface mount component. I'm going to go ahead and make it a little bit bigger, right? Sometimes with the surface mount components, the rectangular ones, you can make the rectangle a little bit longer so that it's easier for you to get the soldering iron on it and then let it just sort of wick down to the pin, you know? So what we got to do, so we got to go to the data sheet again. So we're going to flip over. So watch this. We got to go find the data sheet. Oh, wait, no, we don't. We're going to go over here to our schematic editor. We're going to hover over the top of this, and we're going to come down here to data sheet, and we're going to click this, and boom, there is our data sheet. See how nice that is? And now we can scroll back down to where our dimensions are, and we can start checking this thing out. So like I said, this is going to take some time. You got to kind of focus on this. You might even want to print it out if you don't want to keep scrolling back and forth. But for the first part is relatively easy. We're going to look here, and what we want to know is this little e, the spacing, the center of the holes, right? You could look at this too, but it's just, you know, you get it, right? So e, little e is 2.4, minimum, max 2.7. You see, so they've got even a little bit tolerance in their manufacturing. So if we went 2.5, we'd be pretty spiffy, okay? So that's what we're going to go ahead and do. So now we'll flip back over to here. And unfortunately, you can't, they don't have just like a constraint or measurement tool or something like you would in, say, Fusion 360 or something, right? A CAD program. So what you've got to do is you got to come up here and change your grid size to something that's going to allow you to get the dimension you want. And so if it's 2.5, I can do that with 0.5 millimeter increments. So if I scroll into here now, if I've got a pad right here, here's 1. Okay, so there's 1 millimeter, there's 2 millimeters, and there's our 0.5. So I need to move that. I got to count again. I looked over here. So there's, ready? So 5, 10, there's 1, 1.5, 2, 2.5, right there. So that's where we need it. Okay, 1, 2, 3, 4, 5 things over. 1, 2, 3, 4, 5. You see? Okay, now let's go back and take a look at the hole size. So we know with these ones, we would hope, well, I don't want to say we would hope, but you probably have touched one of these before, and you can kind of get it from what you're looking at here, but maybe not. These are not round pins. These are flat, right? So if you've never held or seen a MOSFET or a TO220 package, then just know that it's a flat pin. So we look here, we want the B dimension, the little b dimension here, and you see the C dimension. So little b and C. So B is somewhere between 0.61 and 0.8. So if we went 0.75, we could be okay that on B. And C we kind of don't care about, because you can look at that to corroborate what you probably already thought, that side's thinner, right? We're not going to make, we're not going to make a rectangular hole for this. So we're going to make a round hole, and it needs to be big enough to be able to put this into it and not have a big, bunch of space there for the solder to go running through. So matter of fact, if the max it could ever be is 0.88, why don't we make it 0.9? Maybe even a millimeter, Ooh. I mean, you could. That could be okay. You might find, if you skirt, let's go 0.9. So if it's skirting the edge right here, it might be kind of a tight fit. And you'll figure that out as you go. You know, you'll maybe take some notes and know that, hey, you know, the last 5 TO220 packages that I've been making the pins kind of tight. I should maybe open them up a little bit. Okay, so we'll make them 0.9. We'll hope that that works. So you come over here, hover over the top, hit E for edit, and here is your hole size up here. So you say 0.9. And now that, of course, reduces the size of copper, the amount of copper we have to get a hold of there. So we can make the diameter bigger, right? But be careful that you don't run into the ones next to it. So say I went 3. It didn't just shrink the hole in the center. It just keeps scaling. So everything, it kind of zoomed out, if you will. And there's our pad. Now, if you do this, you see what's going to happen here? They're going to run into each other, and that's not going to be good at all. So we've got to change that. So it was 1.5. Let's maybe make it, let's try 2. We'll see how that looks. Okay, so 2 looks like it might be okay, but let's take a look. Make another one next to it, 2 also. And so you see this. Now, it looks like, I mean, there's definitely a gap there, and that's cool, right? But how much of a gap is it? Well, remember these spacings right here? This is 0.5 millimeter. So it could be fine, but this might not give you, you know, if you're not soldering well, you might easily bridge this. So you might want to knock that down a little bit. And so to be on the safe side, and you again, you work it out how you want to work it out, because maybe you don't like having too thin of amount of copper there. And also the thinner the copper, you know, maybe the easier it might be to rip off. But remember, this is through hole, so it's going through the other side. So it's got a pretty good anchor there. Boy, I'm talking and blurring. What did I just make that one? I didn't do anything, did I? I think I changed the position. Crap, what the heck? Yeah, I moved the position over. Anyways, there is something you can do as well. So if you don't want to count the dots, you can just put the X, Y position in right here. Cool, meant to do that. Yeah. Okay, so we'll come back here. Let's make this 1.8. And I'll edit this one. 1.8. Now what you could have done, what I could have done, is I could have made 1 first. Say if you got a lot of pins. With 3, this is fine, sure. I really had to do at least 2 pins so I could kind of get an idea of the spacing between them and see if I felt okay with it or not. But if I had to do 100 of these, well, okay, let's say not 100. Say I had to do like 8 or 20 of these. Then you'll get a couple of these sized all out right. Oh, I got to change the holes there that you see too. I get them sized out, and then you could go here. Where's our... Right? And so I could copy those, or I could... where's my duplicate? There. Control D. And then just do the next, the next, the next, right? Here, I'll show you. So we get rid of these, get rid of those, and then I'll just hit Control D, put one right here, Control D, and put another one right there, right? And our spacing should be okay. And again, if it's not, come back here, check it out, minus 2.5. Over here, edit this one, minus 2.5. Technically, oh, it's the same one. I was going to say that should not be minus. It should be a positive on that side. There we go. Okay. So that's it. That's it for our pins. So now the next thing we have to do is go look at the data sheet again. We've got to figure out what the length of the body of the package is. And we also have to kind of do our best to allow for a bend that's going to happen in here. Now down here, where this pin starts to get fatter up here, this is about where it's going to bend over. So this will be in the hole up to, say, close to this thicker area here. And you're probably going to want to bend this on purpose first, just to get it into a nice bent shape. You can take your pliers and kind of make a nice crimp bend right here. So you don't want to solder it in and just sort of like press it over, because it's going to want to spring back up. And if you're just going to use some thermal adhesive is okay. But I have noticed things like whatever. If it does get really hot, sometimes the stuff pops back up. Anyways, you don't need to have any kind of preload on it. So bend these things first. So then you look it up here. So here's the size of the main body right here. But let's see. Here we go. D. D is the dimension of the main body. But we need to know this. Think plus Q. So we'll need something like that, right? Because I don't see any other dimension really around here. Do you? I don't see it. Yeah, we got D. J is this distance. Yeah, so we're going to take L2 right here that goes from the bottom of these up to the center hole right here, and then add on capital Q. So L2 with Q. What did I say? L2. I don't see L2. Okay, well, how about we do this then? So we'll take L1 with D, because D is the main body here with the length of the thicker extensions down here. Okay, let's try that one. So we get our L1 right here and D. So D is gonna, should we go for the high side here? So we'll say 15.75. I mean, this is millimeters. We could just round that up to 16, because again, this is just an outline. And then L1, 4. So, I mean, if we wanted to, we could just round this up to 20. You know, that would, 19, 20. Seems okay. Yeah, let's just go with 20 on that. So that gives us our height, if you will, our length, I guess we'd call that. And then for the width of the thing, that's going to be E. So capital E right here, 10-ish. Now, again, the reason why I'm not worried about accuracy, well, super accuracy, I like the things to be a little bit bigger. So when it's laying down on it, you can kind of see the outline around the package, so you know that it got set in the right place, I guess. So if we went with 11 or 12, I'm going to say 12. So we'll go 12 by 20. Now we need to make a 20 by 12 box around here to tell us where the part is going to sit. But, I mean, that could suffice, but we probably want to make it look maybe a little bit more interesting and provide, of course, some valuable information in this as well. So what I'm going to do first is just lay out the 20 by 12 box, and then we can kind of start cutting back from there. Now we can do this at least a couple different ways. And I was kind of thinking about it before starting here, which way is exactly the easiest. So let me show you. I can come over here and add a line. So it's like a polyline in any CAD program. It's just going to keep going as you click. So see, if I click, 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 it just keeps going. You hit escape and it clips off that last little thread. Control Z, Control Z, Control Z undoes each segment. Now, I have to draw this box, but I don't exactly have, constraints per se to lay it out here. Now, what I could do is I could, if you come in here, we'll get in we don't want to get too close because 20 is going to be off the screen. But we know that right here at 2, this is 0, and so I could draw a line just somewhere like that. And then you could come back here and you could edit the line, get right over the top of it, hit edit, and see we've got some ability here like we could with the pad to put it in a different position. So X is this direction, Y is going this direction. So our starting point is going to be -6. Whoa, what am I typing? -6. And the starting y point is going to be 0 because we want it right on that. Okay. Then the end x point is going to be 6, and the end y point is also going to be 0 again. You do that. You hit OK, and it's going to place it for you. Now, here I guess was my hesitation in doing that. Was that any easier than going over here? You'd set, can you see up here my grid is set at 1 millimeter increments? So I come here and I go 1, 2, 3, 4, 5, 6, click, go back to center, 1, 2, 3, 4, 5, 6, and then clip off the thread there. So was it easier? I don't know. Now, if the line itself was something like 16 1/4, then maybe it might have been easier rather than divide this thing up into, you know, 1/4 millimeter segments or something like that. Yeah, it's probably easier to type it. Now, since we happen to have this already here, though, watch this. So this is pretty cool. It's got some kind of dumbness to it too, but you'll see here in a second. Since the line's already here, I can hover over it. I can hit E for edit, and you can see that your start point is -6 and +6. That's the length of it. And now our starting point Y, well, we want this to be 20, but here's the deal. And I did some quick Googling on this because it's always been kind of dumb, but never really, you know, had any reason behind it. Well, as it turns out, nobody really exactly knows, except for maybe it comes from an old screened Cartesian coordinate system. In all CAD programs and all things across the board and all CNCs, you have your what they call the right-hand rule, if you want to look at it that way. But Y goes like this, X goes like this, which is true. This is what this is doing. But X positive is this direction from 0, right? So if you look at it that way, that's going that way, and X negative this way, X positive should be going this direction, but it doesn't on these programs. So if I want this to go up 20, you have to say -20, -20. And that will put our line up here, you see? So sweat that out, all the people that deal with CAD programs. I don't know, you'd say, oh, well, it's backwards. No, it's not backwards. Y is inverted. If you look at your hand, you do the right-hand rule or left-hand rule or however way you want to do it. You hold your hand out here, you take your coordinate system, you turn it around. If we just flip the coordinate system, then the X positive would be going this way and the Y positive would go in that way. So anyways, whatever. This is the way that it works, and everybody just seems to get used to it. So back to my point here, maybe in working with a line here and typing in the coordinates, it's not perfect. It's not maybe any easier, but why not a little of both, right? So now that I've got my two lines there, now I can just connect the dots. You see? And then over here to over here. Clip that off. And there is my 12 by 20 envelope. So this is just, at this point, it might be done, but I'm going to say it's just a guide for the stuff that I want to put inside here because I want to make it look a little bit nicer. I want the end user, the person that's doing the soldering, to look at this and go, oh yeah, that's absolutely a TO220 package. So we'll come back to the mechanical drawing here to talk about kind of this bend that's going to happen here, and beyond that, the placement of this hole, because this as far as making things look pretty, we can lop the corners off here of our box and kind of make it look like the TO220 package, and maybe even draw a line here to say, hey, this is where the body of it is and this is where the tab goes. But critically, if we're going to put a hole through our PCB right here, this hole needs to be pretty accurate. We need to have this right at the right distance from where those holes are so that everything lines up. Now follow me with this. We're going to take these pins here and we're going to bend them down. We're going to right up to this flat right here. that's where it's going to go into the pin. It's going to sit right there. It's going to hit. Then we're going to take this leg and we're going to bend it over, you see, and there's going to be a little bit of a bend radius there. That we're going to have the thickness of the pin right here, and somehow from here we've got to calculate, after it's bent over in the holes here, how far away from that point is this hole. Does that make sense? So let's go a little bit further here. We've got L1, and then I want to draw your attention to J1 over here. So L1 and J1. J1 is the distance from the bottom of this pin, inside edge here, I guess, face, to the bottom face of the TO220 package. Okay, we come up here. J1 at most, let's say it's you know, like 2.5 millimeters, 2.6. Okay. L1 is, you know, 3.8-ish or something like that. So off the top of my head, you know, it gives us like a millimeter or something to play with. Which, so now if you think about this, if you took this pin right here and you bent it down, a good portion of this bend is going to get ate up by this J1 value. You're going to take this, you see how things are lining up here? Here's the end point that goes into the pins, and then this right here. This is important. This piece right here, that's where you're going to bend it. You're going to bend it right here. This is going to swing down and be almost flush. It's probably going to be sticking out. If you were to bend it right at that joint right there, this right here should almost be flush with the bottom, which is going to create, you know, like I said, maybe a millimeter beyond your D value right here, which is the main, you know, body length of the whole thing. You see, it's kind of a little bit tricky here. And if you had one in your hand, you know, they're not too expensive. If you want to desolder one off a board or just look at one that's on a board already, it's easy enough to go grab a caliper and measure it and see what they came up with. Now, so having said that, what's D here? So D, again, is, let's say it's going to be on the far outside. Well, yeah, we could say maybe 16, and then add on another millimeter for that bend right there. So maybe 17, maybe 16 and a half that will go from the holes to the end of this. So with that value, it does seem like the height of our total box is a little bit longer than it needs to be, but that's okay. But like I said, that was just a guideline, right? Now we're trying to get a little bit more detailed about the thing. So if we want to try to give this our, you know, a good amount of braining to try to figure out what's going to happen here, if you took this L1 value and you bent it, like if you just smashed it somehow right up against the edge of the package, you're going to have the D value plus at least the thickness of C to the, well, half the thickness of C, I guess you'd say, which would be the center of the holes here. And that's probably not entirely, you know, accurate that you're going to be able to bend that, smash it right up against the side there. You'd almost have to cut it and glue it to it, right? Because the bend radius is going to cause it to stick out just a little bit more right here. Do you see? So it's I mean, we're doing our best guess here. And then ultimately, after we figure out, do we just kind of decide a little bit more accurately on what that dimension is going to be, then we're going to subtract Q from it, and that will tell us where that hole position is, okay? So it's a fair amount of work here to try to get that where we want it, right? We can't exactly guess on this. So again, the D value, this time let's get a little bit more, we'll bring out a calculator here. So we've got our D value, which at best, at most, is going to be 15.75, right? So 15.75. And we will add onto it the length, or the width, I guess, of the C value right here. And so at most 0.7, we'll give it that. We'll give it that at most. And then, you know, 16.45, give it maybe another 0.5 millimeter or so millimeter of bend radius right there. So we're still, I mean, we're pretty good at our guess, you know, that we're about 17-ish sticking out to where the hole's got to be. So I know I said accurate and then I said ish, but I mean, that's kind of what we're left with here. So we'll come over here and we're going to place that hole from here because I think that that's our next critical feature. And then any pretty that we want to add to this can go around the critical. So to make a hole in here, if this was a PCB, we would be going over here to edge cuts, but they won't let you do this in a footprint. So the way you do this is you make a pad. And so this is going to be kind of the vehicle for creating the hole, a mechanical hole through the PCB that we could screw this TO220 package down to. So you go ahead and place this. Now we could count up all the dots that we needed to go, but like what we just did, we can come over here, hit E for edit, we'll put it 0 on the 0x, and then for the position on Y, the nice thing here is if we wanted to say 16.95, exactly what we came out with, we could do that. Sure, why not? Or we could just say close enough to 17. But you'll put that there, and again, remember it's minus because it goes backwards. And then we'll just hit OK. We're coming right back, but just hit OK to see that, see, it goes right where it belongs. So then the big trick is we want to take this regular through hole feature pad, and we want to turn it into just a plain old hole in the board, something we can screw something into. Now, if you wanted to have contact from one side of the board to the other, then yeah, you would leave it as a through hole because it gets plated. It gets plated through the middle of this, and so then you would establish contact from top to bottom. But in this case, let's say that all we care about is making a hole through the board. So you're going to come up here, and we have a few different types of pads that you can choose from. So we've kind of already looked before at SMD. So this is your surface mount. There's no hole, right? It's your surface mount pad, and typically you would change it from that to, say, a rectangle, and maybe even change the width and height of it. You could do a connector down here, and a connector, if you look as I flip back and forth between that and an SMD, nothing really seems to change, but if you notice right down in here, the paste layer will go away. So that's basically the big difference there, and they use it for card edge connectors. And then the last one on the list here is the non-plated through hole, and it says right here mechanical because they're thinking it's just for a screw. So you go ahead and you do that, and that gives us this. Now you're going to change it. We're going to change it back to a circle, and then come over here and change the hole size. So the hole size, if we look back over at the data sheet, is at a max 3.85. So that basically tells me that they're accommodating an M4 fastener, which is what we'll go with. You don't want to go in the middle of it this time. You want to definitely go as big as the biggest hole might be, I guess. So we'll say 4 millimeters here. Now, since we're not plating it, we don't really care about the size of the pad. But if you just hit OK, it's going to pop up and tell you you can't do that because the pad is smaller than the drill hole. It's going to chew it away. But if you go ahead and just make it the same size, you can make it bigger if you want. If you wanted to add a little bit of a pad, but it doesn't really seem to make any sense if there's not going to be plating through it. But anyways, you can make it the same size, and we are done. So this is our last critical feature, and now we can kind of move on to making it look a little bit nicer, I guess. But I did want to talk about one more point of interest having to do with holes, the pad size going around it, and this thing called the annular ring. So right here, again, this is a through hole. There is no extra pad on the outside. And when I keep saying this extra pad on the outside, like right here, the yellow area is that extra pad, well, that is the annular ring. And so if they're going to drill a hole through this, you want to make sure that the pad diameter, annular ring, is large enough to where if they screw the hole up a little bit, it's not going to be on the outside of your pad. So for example, if that's my pad I just made, it remembers from the last one you did. Let's say it's a through hole, and we'll say that it's a 2 millimeter, and it's got a 3 millimeter diameter of a pad this dimension right in here, that's your annular ring. So now if I hit OK, well, you look at the diameter of this hole, and the likelihood of this being exactly in the center, well, it's probably not going to quite be perfect, especially if these things, you know, are really tiny, like the micro vias or just small vias that you see. So if it's very vital that you end up having okay, you can't get it spot on in the center every single time. But what I'm getting at here is if you want to make sure that the thing that is paramount is that you always have a complete continuous ring around this pad, make it larger. Make it large enough to where that's going to be, you know, if the drill moves a little bit, it's very unlikely that it's going to make its way out of the annular ring. Okay? So then inversely, if we were to do something like this, that is almost assuredly going to end up being broken. Then looking back here, going back to our first conversation about measuring everything very carefully from this distance to this distance, and how big of a diameter this hole should be, and how carefully we place it, and how those tabs get bent over. Well, when you have all of that information that we had there, when we have all of this going on here, and this potential slight but amount of randomness as far as where this thing gets bent at and where this hole ends up being lined up, and now the possibility that we know that the PCB manufacturers might not drill the holes exactly in the right spot, it's not going to be way off. But just putting that all together, you kind of want to build a bit of some extra tolerance into all of your stuff. I think I'll add in the easy stuff first. So there is the little corners. Come on, there's my little corner. There's nothing on the data sheet saying exactly where to put that, so I'm just putting them up there. Looks about right. The last two things are going to be, we'll have a line that goes across here that's going to show you where the tab is, and then another line that's going to go across here to show you where the body of this ends. And you could just do it like that and leave it be, and that might be good enough. But if we want to let our OCD go out of hand a little bit, we can look back at the data sheet, and there will be a dimension for this. Now, I have to mention that our original design here of the 20 millimeters from end to end is not exactly so correct. So there's going to be a lot of dimensions you're going to see that are based upon, like this hole is based upon the top edge and et cetera, right? But we measured it from down here, which is good. But this line, for example, right here where the tab ends, H1, it's measured from the top edge. And D also from the top to the end here. And we're keying everything off of the holes that we place. So we've got to kind of make at least a pretty good assumption on what this extra value is right here. We've been saying it's like 1.5 millimeters or 2, we could say 2 millimeters, that it's going to stick out after it's bent. So for example, let's say H1, let's try to attack that one. So H1 is, let's say, 6.5 millimeters. So 6.5 millimeters from the top here. Wow. Need to write this all out. Subtract that from the D value. So our D value here is, say, 16. So we're going to say 9.5. 9.5 from the bottom edge of the part here. 9.5. 10.5, 11. Let's say it's 11 from the holes. So then you come back here, get right over the top of the hole there, hit E for edit, and then you say minus 11 for the Y value. You see, then there's the tab. Now we can do the same thing for this, but this one we already kind of know. We already know that it's going to be whatever we committed to, saying that maybe we'll give it about 2 millimeters away. This is just aesthetics mostly, but like I said, we're letting our OCD kind of go a little bit on its own. So let's say that's our part. Then maybe the last thing I want to do, because it'll give me a chance to talk about something else as well, is I want to draw a little line from this end of the body here to denote that this is where the pins go here and they're bent over. But as you can see, I can't get to any points in there. So what you need to do is come up here and change your grid spacing. We'll just knock it down half of what it was. So 0.5 millimeter spacing. And now that'll put a dot right in the center there. So I can now go click to here. And then I can do another one from there to there. And then another one from there to there. Okay? And I think that's done-ish. To make it look more correct, I guess I'd say, we got to get rid of all of our reference lines. There's too many dots. I'm going to turn that back off again. And I'm going to move this out of the way. So we'll put this up there somewhere. Wow. Out of control. And we'll take this right there. No, not that. That. And we'll move that up here. Then we got to come by and delete all of our guidelines. So we'll grab our garbage can here, and you come over, get really carefully on the line there, and you can delete it. But you see what's happening is it deletes, well, everything goes away. But that's okay. We've got enough information there to redraw what we want. Come on. Okay. And then reconnect. Maybe you'll put this back here now. Maybe put it off to the side like we talked about. And then this right here doesn't really matter because that's going to be invisible. So there, finally, is our footprint. And then before we forget, well, we have to do this. We probably should have done it somewhere along the way. Save your footprint in your active library. Come up here, hit save. There's your library. Done. So that's the whole process. A couple more things, and then we're out of here. This that we created before, remember how you could come over here and you could hit edit? Well, now that we have a footprint, you'll see that that's in here, and all I have to do is say browse footprint, and there it is. So now they're connected. And so then if I were to come up here to do the assign PCB footprint and to do the association, you click this, and if you scroll down here, look, now we already have our symbol associated with our footprint, so we don't have to do that. So if you went through and for all of the components that you use in all your parts, at least for the most of them, you make your own footprints, make your own associations in here, then you don't have to do this whole part any longer. So that's a really nice thing as well. Another thing I thought I would share or show or look at is if we go back to footprint editor here, let's bring up, not ours, let's bring, oops, I didn't mean to do that. We'll go here and we'll select by browser and we'll scroll through here, and if you get down to packages, you'll find TO SOT through hole. And keep scrolling, scrolling, scrolling until you get to TO223. Yeah, 3-pin, tab down. We click that. Look, not a hell of a lot of difference, even including the little legs down here that I just sort of did, you know, kind of sort of arbitrarily. And I did just drop the reference off to the side there. It does make a lot better sense to put up here or maybe down here. And this one here is hidden as well. They've got a mechanical hole running through. So, we did good. So go ahead and give all that a try. I do want to mention how really important it is to get this done, to get really used to this process, because making your own footprints, maintaining your own libraries and your own symbols is probably, I'd say, critical to you in a company type capacity, or even if you're selling anything. You don't want to be relying on other people's footprints and libraries that come in and out because, you know, somebody made a change and it updated from GitHub and then something's maybe not working right. You don't, whatever, you just don't want to trust it, so you want to do your own thing to rule all that out. For review, what we started with was, well, a need to create a schematic symbol. We came here to create our schematic symbol, but found out that we needed to make a library. We made our libraries in our computer. We made a folder in our computer where we'd store these libraries. We named it with a symbol or something like that so it would alphabetize properly, get up there easy to see. Once we were in the footprint editor for our schematic symbol, we discovered how to make pins. So we made our pins here, put them in the right direction, and gave them a purpose. Was it a power input, a power output, or whatever, and a label that went along with it. Again, consulting the data sheet to make sure that all of this was true and correct. The data sheet labels it 3, 2, 1, just like this. We gave it a name for the device that would get annotated and come up as, in this case, Reg 1, Reg 2, and so on and so forth. We learned how to hide certain things, make them invisible. You can see it here, but when we're outside of the editor, you don't see it here. Then the next thing we did is go into our footprint editor, which also had to have a library created first before we could go on. And in this case, though, we learned about going up to manage footprint libraries, and we stored these libraries inside we stored these footprints inside the same computer library that we had our other ones, so that everything would be in one location. We also talked about separating them. Once we got to here, we started consulting the datasheet for the mechanical properties of this, as in where are the holes placed. How do we place them? Well, we make a pad. You make a pad of a certain hole size depending upon the pin thickness of the part that you're putting into it, and then creating enough of an annular ring we learned about to give you enough room to where if they misdrilled the hole, you'd still have enough pad left over, and just in general enough pad to be able to solder to. Again, labeling these pads correctly so that these numbers here match up with the numbers on the schematic symbol that we created earlier, so that when we go to route and connect things, it makes sense. We learned about non-plated through holes, in this case right here for a screw hole to go through and bond it to the board, more graphic lines that we created, and again, reference numbering and being able to hide features just as well. Oh, and also learning how to move things through our XY coordinate system and understanding how our Y system is backwards from most CAD systems. So a lot of stuff that we went through in this one, which I really thought was just a short, easy, simple, basically video on graphics, because I thought it was going to be like, yeah, make a line, but as usual, massive amount of devil in the details. So again, go out and do this, make some boards. The next videos coming up will probably be something on some real simple basic routing. And after that, I want to do something that I was doing recently, which is how to combine other PCBs into one PCB so that you could make the best of your size that you're allowed of with places like Seed Studio, so that you could send off maybe 6 or 8, different small PCBs on one board and then just cut them out. So, happy holidays, everyone. Hopefully this helps you. Remember that Chinese New Year's is coming up, so you've got about 2 more weeks, maybe 2 weeks, to get these boards done that you're going to be building and get them turned in if you expect to have them back anytime soon.